After understanding the first order differential equation in its standard form, now we'll discuss various cases that are possible. The first case is homogeneous case, and then there will be non-homogeneous cases as well. But recalling the standard form, it was this, where a and b, they were the constant coefficients and constant terms respectively. Now we consider this case, that is the homogeneous case, in the beginning, and there are two other cases that we will discuss later on. So the homogeneous equation is one that has a 0 on the right hand side. So if b is equal to 0, the right hand side becomes 0, and in that case we can call it a homogeneous case of the first order differential equation. Contrary to it, if the right hand side, that is b, is not equal to 0, we will call it a homogeneous case. However, a can have a different value here. One possibility is that a is not equal to 0, other possibility is that a is equal to 0. So it gives rise to a couple of non-homogeneous cases, that is non-homogeneous case 1 and non-homogeneous case 2. So there are total 3 cases. Fourth one is when a and b both are equal to 0, and when both of them are equal to 0, then dy over dt will become equal to 0. If you put a is equal to 0 and b is equal to 0, for example in this equation, that is this, if you put it like this, it will become dy over dt is equal to 0, which means that there is no rate of change. And when there is no rate of change, it means that the differential fades away, and when the differential idea or the concept is not present in an equation, it doesn't remain any differential equation. So this possibility where a and b both are 0 is not considered here, because it removes the presence of differential equations. So now we focus on the first case, whereas we will talk about the second and third cases afterwards. So here a will be non-zero and b will be equal to 0. After assuming this, we can put the value, that is 0 here, and it shows that it's a homogeneous case. Now we can rearrange the given equation in a way that will allow us to cancel out and settle the equation in such a way that will allow us to integrate. So if there is anything to shift or cancel, we can do that. Here we can see that y is on the left hand side and t can be put on the other side. This is one way of doing it. You can see these steps where the rearrangement has given rise to this form. You can see that the derivative is in the numerator and the function is in the denominator. So now if we integrate them with respect to t, you can see the integral sign is introduced as well as the dt. It will give us this form after cancellation, as we mentioned earlier. Cancellation is possible. dy over y will be the form on the left hand side. So we can write it like this, and this means that it's equal to the natural log of y, because it is the derivative over function situation here, derivative of y with respect to y, and y itself. So it becomes 1, as you can see, and y remains y. So we have done this before in the integration of such a situation where the numerator has the function and the has the derivative, and the denominator has the function. Integration causes c1 and c2 on both sides. Here we can integrate this constant and get at, where the minus sign is still there and it was there before. So clustering these two constants here, we get a difference of constants, which can only yield a constant on the whole. That is another constant which we can represent with c. So now it is arranged in this way. We are in search of the solution that should be in terms of t, and it should be of y, not natural log of y. So we want to get rid of natural log. For that, we know that we can raise it to exponent, because exponent and natural log can be cancelled out, and they are cancelled out on the left hand side. However, on the right hand side, the exponent gets disintegrated into two parts, because both of them have the same foundation, that is exponent, and Now exponent of c is another constant, because if I take the exponent of a constant, it will remain a constant and it will not turn into any variable, so it will remain a constant. So we represent this constant with a. Instead of writing this form, a is a single notation, and then we can rearrange it. We can write a here, and we can write exponent of minus at, as you can see, it's just brought from the same step. um, it is the general solution. Why it is a general solution? Because a is there, and we know the concept of arbitrary constant, that it is neither known nor determined. So this element of arbitrariness is still there in the given in the found solution, so we call it a general solution. But we know we can try to definitize it, and for that we use the initial condition, which means that we are to substitute t is equal to 0, and when we do so, um, wherever we can see 0, we will put 0, as you can see here and here in this general solution, and then we can simplify it. By simplifying, we will get a's value, and the value of a is y naught, so we can put it back into the general solution, and it will make it a definite solution. We call it a definite solution because y naught is a known value, a determined value, and it's also known as the initial condition, because it is the situation when no time has passed, that is now. So it is an important thing to know, because it allows us to understand the graphic situation of the solution of the differential equation. So arbitrary constant is determined, and now we have a definite solution which is clear, where there is no element of arbitrariness and which is not general in nature, and will allow us to make a graph which will be based on the numerical values, and there will be a certain beginning point as well. Thank you.